The research addresses the challenge of detecting obscured wildfires using drones equipped with RGB cameras. It proposes a novel methodology employing semantic segmentation based on the temporal analysis of smoke patterns in video sequences. The approach utilizes an encoder-decoder architecture with a pre-trained CNN encoder and 3D convolutions for decoding, exploiting temporal variations. The method achieves a DICE score of 85.88%, precision of 92.47%, and classification accuracy of 90.67% on test data, outperforming other methods in video-level fire classification. The proposed method is structured as a deep convolutional neural network, CNN, that uses a pre-trained CNN architecture as an encoder to extract features of video frames and passes sequentially stacked features to the decoding stage. This architecture is designed to analyze the sequence of frames in the video and predict the location of obscured fires. The method's uniqueness lies in its ability to detect obscured fire using temporal features from video frames, which is particularly useful for real-time monitoring and control of wildfires using drones. Here is a combined summary of pages 3 and 4 of the research paper. The proposed method for obscured fire detection uses RGB images at runtime, eliminating the need for expensive IR cameras on site. Ground truth fire locations are obtained from IR images, and a sequence of input frames is used to predict where the fire is hidden. The ground truth is approximated by applying majority voting to the pixel labels obtained from 20 IR video frames, resulting in a single ground truth label for each sample. The network architecture consists of a pre-trained VGG16 encoder that encodes features from video frames, and a 3D decoder that decodes information from the volume of features. The decoder has two parts. The first part decodes information in both the image and time axes, emphasizing the capture of semantic relationships between frames in the time axis, while the second part consists of a series of time blocks and a final convolution layer, capturing information from consecutive frames. The DICE loss function is used to measure the alignment between the ground truth and the detected fire regions, with the objective of minimizing the loss during training. The experiments are conducted using the Flame2 dataset, with 354 videos for training and 155 videos for testing. The model is implemented in PyTorch, tuned for the best hyperparameters, and trained for 300 epochs with a batch size of 5. During inference, frames are taken at a window size of 20 and slid over the video at a stride of 1. The evaluation metrics used include the DICE score to assess alignment quality, blobwise precision to ensure correctness of predictions, and clip-level classification accuracy to evaluate video classification. The quantitative results show the performance of different backbones and attention modules, with the proposed architecture achieving promising results in obscured fire detection. The proposed study introduces a novel approach for detecting obscured fires in real time using video feeds captured by drones equipped with RGB cameras. It leverages pre-trained CNN architectures and 3D convolutions to create temporal feature maps and uses attention modules to predict fire regions through sequential analysis of video frames. The methodology was evaluated on the curated Flame2 dataset, which utilizes IR images to determine ground truth fire regions, and showed promising results, improving fire detection accuracy compared to state-of-the-art methods, achieving near 100% accuracy, and successfully detecting invisible and covered fire region borders, approximately 85% in DICE score. The paper also discusses the use of various backbones, including VGG16, ResNet18, Efficient NetB0, and MobileNet, along with different attention types such as CBAM and SCSE. The results indicate that Efficient NetB0 with SCSE has shown a similar DICE score and superior performance in blobwise precision. ResNet18 plus CBAM and MobileNet plus CBAM have demonstrated 100% classification accuracy. The study's qualitative performance is demonstrated through figures, which show the model's ability to detect both visible and obscured fire regions accurately, even when they are obscured by trees and smoke patterns. This methodology allows for utilizing firefighter drones to combat wildfires more efficiently by targeting visible and invisible fire hotspots. It also helps detect fire regions precisely without the need for IR cameras in the test phase, significantly reducing fire monitoring costs. The paper highlights the potential for future research, including refining and expanding the methodology, considering other environmental factors that may affect fire behavior, applying the approach in practical scenarios, developing onboard processing software, and integrating with existing wildfire management systems. The proposed method utilizes a deep learning architecture that integrates pre-trained CNN architectures and 3D convolutions to create a temporal feature map and use attention modules to predict fire regions by the sequential analysis of video frames. This approach demonstrates great success in detecting invisible and covered fire region borders and allows for utilizing firefighter drones to combat wildfires more efficiently by targeting visible and invisible fire hotspots.